Alright, hello lovely humans, Jen Foxbot here for what turned into part 3 of derivative calculus. But I want to break these into smaller chunks so that you can more easily pause and go back and identify the different pieces of learning math things. So in part 2 we reiterated the power rule a little tiny bit, and we learned the sum rule, which is pretty straightforward, as well as the product rule. Okay, so I left you with a challenge, and I was a student that really benefited from having solutions so that I would know if I was on the right track or not. So after simplification, this is what I got when I took the derivative of f of x times g of x. So I just, if you did that challenge, go ahead and screen capture or pause the video and check your work. So I'll read this in case my handwriting is hard to read. So I got 3acx squared plus, in parentheses, 2bc plus 2ak times x plus kb plus c squared. So I separated it into kind of 3 pieces. So we have the x squared first, and we have the x term second. There are 2 of those, 2 different ones. And then we have the constants at the end. And remember, A, B, C, oh, I used the same constant. That was a bad choice. But, oh well, haha, too late now. Anyway, so this C, yeah, there are 2 different C's. Ah, good times. This is when you would plug in numbers and then solve and all that good stuff. So, yeah. Whoopsies, keeping you on your toes, one variable at a time. Okay, so anyway, now we are going to cover the quotient rule. So the quotient rule is very similar to the product rule, and we'll use these as an example, although I'm not going to run through the whole thing. So we'll say that this is rule 3, so the derivative with respect to x of, f is on top, f of x times g of x, or divided by, that's not times, equals, okay. And so this is where I'm looking at my notes, so you know that I don't actually have these memorized. I just know how to employ them, so when I need them, I just look them up, and it's no big deal. If you do need to memorize them for a test, just practice them a lot of times, at least 20 times, and you will have it down. It doesn't need to be complex equations either. You can go even more simpler than this. So I want to make sure I get this right, so I'm going to look at my notes while I do this. So we have f prime of x, the derivative of x, times g of x. Oh shoot, I'm going to run out of space. Okay, hold on, let me write this a little smaller. F of x over g of x. Okay. F prime of x times g of x. So this is similar to the product rule on top, except now we have a minus sign. And we have f of x times g prime of x, or derivative of g, divided by g of x squared. So that's kind of interesting. That's the big difference. And then this minus sign right here. So g squared of x is going to be this squared. So if I were to do that really quick, it would look like cx plus k times cx plus k. We're going to get c squared x squared plus 2ckx plus k squared. So you would just plug that in on the bottom. That is the quotient rule, aka what happens when you have 2 functions divided by each other and you don't want to simplify, because I don't know if that would be possible to simplify. So this equation is how you would take the derivative of something like that. Okay, and then the last type of rule that I am going to cover, and I'll talk about this in more detail because it can actually be a little confusing. So the chain rule, I guess I'll title these. Oh, shit. Keywords are fun. Okay, and then this is the chain rule. So now we have the derivative of one function of another function. And before you're like, what? We'll talk about it. Okay, so this equals the derivative of x f of g times g prime of x. And so this chain rule, even though it looks a little funky, is actually super useful because you can apply it to a lot of different scenarios. So what does this mean? What is f of g of x? It's okay. Just remember that this parenthesis basically means we can put whatever we want into this function and it will give us this result. So I could say, what is f cat, meow, meow. And then you would say, well, it's a cat squared. I don't know what that means, but sure. Meow. Plus b times cat. Again, don't really know what that means, but that's cool. Okay, whatever. Plus c. Okay. So yeah, that is a perfectly mathematically acceptable thing to do. You might ask, well, how does this apply to real life? And like, I don't know. And that's okay. For math to be cool, it doesn't have to apply to real life. When you're doing physics, then you'd be like, does that mean Schrodinger's cat is alive? I don't know. But anyway, so yes. So that basically just means when we're asking what is f of g of x, we plug in g, which is this, into f. So f of g of x is this chunk in for x. So we would get a times cx plus k. You know what? I feel like I should change this variable at this point. We're going to call this L. Okay. Keep these things straight. Okay. So Lx plus k squared plus b times Lx plus k plus c. So that is f of g of x. And then when you ask, oh, I see, taking the derivative of that is going to be a little complicated. Yeah, but that's okay. You got this. So what I would recommend when you're doing this is, especially when you're first getting started, you'll start to notice patterns and then you can crank it out, no problem. When you're first getting started, solve the whole thing, meaning, or simplify the whole thing. So what you would do is you would multiply this, you would distribute the b, you would get this function so that it is in its simplest form as possible. Then you take the derivative of this chunk. And then you take the derivative of g. So g prime of x is just, in this case, L. Change my variable. And then you multiply that by the derivative of this chunk. So fortunately, in this case, it's not super difficult to do. I would challenge you to try that on your own. And if you would like the solution to that one, please just let me know, and I'm happy to talk about it. But I think that you are all ready for some other special types of derivatives. So I'm going to really quickly talk about some of the most common ones. So what rule is this? 5? I don't know. 6? Okay. 5/6. I can't remember. Haha! Like I said, I did physics. So, numbers. Variables that are numbers. Yeah. Okay. Okay, so the derivative of sine of x, where sine is like blue. I drew that terribly, but that's okay. Equals cosine of x. And this is actually really interesting because this means that as the function sine changes over time, the rate of change is cosine. That is rad. And cosine looks like this. So it's almost the same, but it just kind of starts at a different place. So I think that's really beautiful. The derivative with respect to x of cosine of x is negative sine of x. And then you can look up the ones for tangent if you happen to need those. Oh, hold on. Alright, sorry about that. My dog was barking, so I figured I would pause the video, because it's kind of hard to hear me talking when he's barking. Okay, so, yeah, if you want to look up tangent, no problem. And then some other interesting ones are when you have x in your exponent. So if you have a constant to the x power. That's a funny way to say that. Xth power. It's kind of tricky. You have the natural log, which is a logarithm with respect to the number e to the 1th power. I like that, 1th power. So the natural log of a times a to the x. And the other really interesting one that if you go forward in physics or in engineering, this will come up all the time. You can never get away from it. It's actually really beautiful because when I switched into engineering after doing physics, I was really surprised and stoked to find that a lot of the mathematics that I had to learn for physics easily translated into engineering. The difference is that we are solving different types of problems, but at the end of the day, the skills in your bag of tricks are pretty much the same. You just have different boundary conditions and the variables mean different things. But I think that's really awesome that once you understand mathematics, you can apply it to so many different areas. Okay, so the derivative of e to the x is e to the x. What? So cool. So this is kind of an interesting problem because I think it goes up something like this. I'm not drawing it, of course, properly, but this means that this function, the rate of change of this function is itself. What? That's pretty wild, right? And so it's used to model different types of natural phenomenon and things like that. And I will give you a quick tidbit that e to the x and sine and cosine can actually be paired when you have complex numbers. And that is a very, very helpful way to solve lots of different problems in the real world. Okay, so please let me know if you have any questions about derivative calculus, if there are particular types of problems that you're really struggling with, or if there are any particular concepts that were confusing. I tried to assume that y'all knew nothing going in, so let me know if there was an assumption that I made that wasn't true for you. I want to make sure that this is accessible for everyone. So yeah, please let me know how you felt about this so that we can all learn mathematics together, because we are all capable of doing that. If we can speak a language, we can definitely learn math. Cool. So thank you very much for watching, and I'll see you next time. Bye!